Now we'll start first with the definition of specific heat capacity. Q is the quantity of heat. It is directly proportional to the mass of the substance. Obviously, greater the mass of the substance, greater will be the heat required to change the temperature of that substance. It is directly proportional to the change in temperature. Either I can write delta T or simply I can write it as T. It also depends upon the kind of material that is going to be the specific heat capacity. So here I'm going to get the equation Q is equal to mc delta T or simply mct. Okay, m is the mass, c is the specific heat capacity, and T is difference in temperature. You can also write delta T over here. Now suppose here if I'm taking the mass of the substance as 1 gram, or in SI units if I'm taking, it will be 1 kilogram. Okay, this is the mass of the substance that is taken. T, that is difference in temperature over here, suppose it is 1 degrees Celsius. It can be 1 Kelvin also. Okay, because the difference is going to be same. So here mass is 1 gram or 1 kilogram, that is unit mass. Change in temperature is going to be by 1 degrees Celsius. In this case, this M becomes 1, this T becomes 1, okay, multiplied by C. So Q, this equation becomes Q is equal to 1 into C into 1. So that is Q is equal to C. And this C is nothing but specific heat capacity. Okay, so how do we define specific heat capacity? C is Q, that is the amount of heat required to do what? For the mass of 1 gram or 1 kilogram to change its temperature by 1 degrees Celsius. Okay, so I'm just going to write down the definition of specific heat capacity. Is the quantity of heat required for unit mass of substance to change its temperature by 1 degrees Celsius or by 1 Kelvin. So this is the definition of specific heat capacity. Now how do we get the units of specific heat capacity? Okay, now Q is equal to mc delta T or mct. This is the formula. So Q divided by, I will bring m down here in the denominator. I'm going to bring T over here in the denominator. That will be equal to C. Now this equation is going to give us the unit of specific heat capacity. Q obviously is the quantity of heat, that is going to be in joule. M is the mass, that could be in grams or it could be in kilograms if I'm using SI units. T is temperature, you can take it as degrees Celsius. So the unit of specific heat capacity, this is going to be joule per kg degrees Celsius. Okay, this is the SI unit of specific heat capacity. The next thing that we are doing is heat capacity. Now how do we define this? First I'm going to get that equation Q is equal to mct or mc delta T. Now here what I'm doing is only simply I will take this T as change in temperature as 1 degree Celsius. So it is going to be for any amount of substance. Okay, so we are going to write down the definition of heat capacity, which is going to be is the quantity of heat required to change the temperature of a substance by 1 degree Celsius or 1 Kelvin. So over here from this equation, if I want to calculate the value of heat capacity, okay, our equation is Q is equal to mc T or mc delta T. What I'm going to do over here is Q divided by T. This is equal to M multiplied by C. This is going to give us the value of heat capacity. Okay. I just want you to copy down all the things. Next thing is we will just do a few numericals based on this. Before we go to the numericals, some more additional points in both of these things. Okay, now what does this value of specific heat capacity tell us? Remember here, lower the value, it tells us that this substance is a good conductor of heat. Okay, it simply tells us that less amount of heat is required to change the temperature of this substance, and higher the value of specific heat capacity, it means that this substance is a poor conductor of heat. The value of specific heat capacity of copper is given to you. That's 0.39 joules per gram degrees Celsius. Okay. We are supposed to find the quantity of heat. That's Q is question mark. Mass of the substance that is given to you is 20 grams. C, that is the value of specific heat capacity, is 0.39. Delta T or T, that is difference in temperature, over here is going to be 53 minus 38. That's going to be 15 degrees Celsius. So directly you can use the formula Q is equal to mc T. Okay, mass over here is 20. Specific heat capacity is 0.39 multiplied by 15.
No, joules, only joules.
It'll be only joules because it's Q, that's quantity of heat. Okay. Now in the same sum, you also find out the heat capacity. How will you get the value of heat capacity? Okay. This is your equation. Q is equal to mct or mc delta T. You just bring that T here in the denominator. That is M multiplied by C. Okay. You can use any one of these. Either you can use here the left side or you can also use the right hand side. Mass given is 20. Specific heat capacity is 0.39. Or you have found out the heat, which is 117, divided by difference in temperature is 15. Okay, just use any one of these parts and get the value of heat capacity.
7.8.
This will be 7.8. See the units. Q is having unit joules, T is having unit degrees Celsius. So the unit is going to be joules per degree Celsius. Even if I multiply 20 and 0.39, I'm going to get the same value. Okay. Okay, the sum is a burner raises the temperature of 720 grams of water from 20 degrees Celsius to 100 degrees Celsius in 10 minutes. How much is the heat supplied per second? Okay, so the first thing is I'm supposed to get the quantity of heat, that is Q. Okay, mass is 720 grams. C, that is specific heat capacity of water, is given to you from the chart, 4.2 joules per gram degrees Celsius. Delta T or T, that is difference in temperature, 20 to 100. correct? This is the difference in temperature. That will be 80 degrees Celsius. Okay, and they have asked how much heat is supplied per second. Now time given over here is 10 minutes. That's 600 seconds. Okay, so the quantity of heat per unit time, this is equal to mct or mc delta t divided by time. Okay, mass is 720 into C, that is specific heat capacity of water is 4.2, multiplied by difference in temperature is 80, divided by time given to you is 600 seconds. Okay, this will give us the final answer. Its amount of heat
Joule.
divided by time is there, that should be in seconds, so it is going to be joules per second. Also remember, this is the unit, joules per second is the unit of power. So basically you can write this as 403.2 watts also. Okay, quantity of heat per second. Joules per second means power. That can be even in watts. Yeah, just read this sum.
40 grams of water at 100 degrees Celsius is mixed with 40 grams of water at 20 degrees Celsius. Find the final temperature of the mixture.
Okay. Now I'm taking first over here hot water on one side, cold water on another side. Correct? Mass I will take this as M1. Here mass I will take this as M2. Specific heat capacity C1 and C2. In either cases, in both the cases it is water only. So both the values will be same. That is 4.2. Okay, joules per gram degrees Celsius. In temperature, I'm going to make here 3 columns. One is going to be the initial temperature, then the final temperature, and then the difference. Okay, this difference is going to be T1 and T2. What is the initial temperature of hot water? 100 degrees Celsius. The initial temperature of cold water is 20 degrees Celsius. Final temperature is going to be same because both water when mixed, they are going to attain same temperature. Now in the first case T1, that is the difference is going to be 100 minus X. Here the difference is going to be X minus 20. The reason for this, taking it this way, is because see, we are mixing water of 100 degrees Celsius and 20 degrees Celsius. So obviously the mixture is going to have temperature which will be less than 100 and more than 20.
Yeah.
Correct? So because here it is less than 100, I am writing this difference as 100 minus X, and it is more than 20. So I am writing this as X minus 20. Okay. Next part is, now the principle that we are using over here is heat lost by hot water. This is going to be equal to heat gained by cold water. Okay, this is known as principle of heat exchanges. Of course, here the most important question that is asked over here is, what is the assumption that you have made? Heat lost to the surroundings is neglected. So now here, heat lost by hot water is going to be M1 C1 T1. This is equal to the heat gained by cold water is going to be M2 C2 T2. This mass is 20 grams. Specific heat capacity for water is 4.2. This is going to be 100 minus X. This is equal to the mass of cold water is 40 grams multiplied by the specific heat capacity of water is again 4.2 multiplied by here the difference in temperature is x minus 20. Out of these 4.2 straight away can be struck. I can also remove 1 0 from 20 and 40 because they are outside the brackets. So what I'm getting is 2 100 minus x is equal to 4 x minus 20. This is a simple linear equation. Okay, so this is going to be 200 minus 2x is equal to 4x minus, this is going to become 80. Just bring this minus 2x here. So that's 4x plus 2x, that's going to become 6x. Bring this minus 80 on the left hand side. So it's going to become 200 plus 80. That'll become 280. X is equal to 280 divided by, that's 46.67. We'll round it up to second digit. Just work this sum on your own. Okay, X, that is final temperature of the mixture, is 15 degrees Celsius.
Find the time required for a
Heater
of power 1.4 kilowatts to change 100 grams of water from 0 degrees Celsius to 30 degrees Celsius.
See, the first thing that we are going to find over here is Q. That is the amount of heat required, which is going to be mCt or mc delta T. Mass over here is 100 grams. Specific heat capacity of water is 4.2. Multiplied by T, that is difference in temperature, is 30. Okay. Now this Q is nothing but the amount of heat in joules. Now the power given over here, what is the formula for power?
Work over time.
That's work divided by time. This work is nothing but the amount of heat. Okay, because work and energy have same units. So work divided by time, this is going to give you the power. Now power over here is 1.4 kilowatts, which is going to be 1400 watts. And second, power is equal to work divided by time. Yeah, it's other way around, sorry. Okay, power is 1400, work done is 100 into 4.2 into 30 divided by time. This T will come over here, 1400 will come down. You just have to make reciprocal of 0.11. So time is going to be equal to 100 multiplied by 42 into 3 divided by 1400. 14 3s are, this is going to be equal to 9 seconds.
Yeah, 9.
Okay. Next part is latent heat. Okay, latent, the meaning of this word is hidden. It means that which cannot be seen. Now latent heat means that's the amount of heat required to change the state of a substance. Okay, now see, for example, if I'm having a melting ice, okay, here the ice is there, you keep a thermometer over here, and of course the heating arrangement is there. Because here it is melting ice, the temperature shown is going to be 0 degrees Celsius. That's going to be the lower fixed point. When you supply heat from here, okay, initially you see, you will be able to see that the ice is melting into water, but you will not be able to note any change in temperature. So although you are supplying that heat energy, but that heat that is being supplied, that is not shown in the form of change in temperature until all the ice has not got melted. There will be no change in temperature. The temperature is going to remain 0 degrees Celsius only. So as the process of melting is taking place, there will be some amount of solid ice, there will be some amount of liquid water, but the temperature of both of them is going to be 0 degrees Celsius only, because it is melting ice. So after all the ice has got melted and turned into water at 0 degrees Celsius, then there will be rise in temperature. So until then the temperature is going to remain constant. So this, if I'm going to show with the help of a graph, okay, this is going to be time and this is going to be temperature. Initially the temperature that is there is 0 degrees Celsius. So until all the process of melting is taking place, this temperature remains constant. At this point, okay, suppose if I'm starting from point A, I have reached here point B. During this stage of graph of AB, the process of melting is taking place. It means both solid ice at 0 degrees Celsius and water, liquid water at 0 degrees Celsius will be present at all these points. Once it has reached B, all the ice has got converted into water. There will be only water at 0 degrees Celsius. Once the process of melting is complete, then there will be rise in temperature. This is going to occur until the temperature reaches how much? 100 degrees Celsius. And then further, then the temperature is going to remain constant. Okay, that is going to be latent heat of vaporization, because here the process of boiling is taking place. And here the process of melting is taking place. So I can make you write the definition of latent heat. Okay, is defined as the amount of heat required to change the state of unit mass of a substance. Okay, the formula that will be applied over here, remember here there is no change in temperature, so the formula is Q is equal to M multiplied by L. M is the mass of the substance and L is the latent heat. Okay, this latent heat, if it is melting, we call it latent heat of fusion. Fusion means melting. Okay, and if here boiling is taking place, then this heat, latent heat, will be known as latent heat of vaporization. Okay, I'll just make you write this and then we'll just do a few numericals. Okay, find the amount of heat required to change 10 grams of ice to water at 0 degrees Celsius. Okay, so here the direct formula is there, Q is equal to M into L. Mass is 10 grams. The value of latent heat of ice will be given, okay, which is going to be 336. Now what will be the units of latent heat? Okay, now Q is equal to M into L, see the equation. So Q divided by M will be equal to L, that's the latent heat. Q is the amount of heat that is in joule. M is mass. Suppose if I'm taking it in grams, then it is simply going to be joules per gram. Okay, if you are taking SI units, in that case it is going to become joules per kilogram. This will be the SI units of latent heat. Just copy down this much part as well. Okay, find the amount of heat required for 5 grams of ice at 0 degrees Celsius to change it to steam at 100 degrees Celsius. Now see here, directly ice is not going to become steam. First, what is going to happen? Melting is going to take place. Okay, so here ice, see the steps of this. At 0 degrees Celsius. This is going to become water at 0 degrees Celsius. This is change of state. So I'll write this Q1. Whenever change of state is there, the formula is going to be M multiplied by L, that is mass into latent heat. Second thing that is what is going to happen is water at 0 degrees Celsius is going to become water at 100 degrees Celsius. Now here change of temperature is taking place. I'll write this as Q2, which is going to be MC delta T. Now water at 100 degrees Celsius finally is going to become steam at 100 degrees Celsius. This will be Q3. Now here again change of state is taking place. Whenever change of state is there, the formula will be Q is equal to M into L. But remember, these both L values will be different. The reason for that is here melting is taking place. So I'm going to use here the value of latent heat of fusion. Obviously this value will be given to you. And here water is turning into steam. So here I'm going to use the value of latent heat of vaporization. So now Q1 mass is 5 grams into latent heat of fusion for ice is 336 joules per gram. Q2, that is MC delta T, mass is 5 grams, C is specific heat capacity of water, which is 4.2 joules per gram degrees Celsius, multiplied by delta T, that is change in temperature. How much is the change in temperature? 0 to 100. So difference in temperature is 100. Of course, I'll calculate this value. Then Q3. Again here, water is turning into steam, that is change of state. So the formula is M into L. Mass is 5 grams only. Okay, latent heat of vaporization of steam, this value will be given to you, which is going to be 2268. Of course, joules per gram. You can just calculate all of these values. Okay, and then you will add them up.
Yes, sir.
See, in the same question, I can additionally ask you one more thing over here. Okay, if I'm using a heater of power, say 1 kilowatt, how much is the time required to bring about this change? Now power is 1 kilowatt, that means 1000 watts. Okay, now power, what is the formula? Work upon time. Work done is amount of heat, that is 15120 divided by time, that is equal to, here the power given is 1000. So I'll take this T up, I'll bring this 1000 down. This is going to be the time. Of course, it is going to be in seconds, which is going to be, I can shift this, 15.12 seconds.